So the next talks is about new upper bounds for evolving secret sharing via infinite branching programs by Bar Alon, Amos Beimel, Tamar Ben David, Iran Omri, Anat Paskin-Chernyavsky, and Bar will give the talk.
Okay, so thank you for the introduction. So I'm going to talk about new upper bound for evolving secret sharing. This is joint work with Amos Beimel, Tamar Ben David, Iran Omri, and Anat Paskin-Chernyavsky. And to start with, I want to start with a story about secret sharing with many homers. So let's suppose that we have a dealer that holds a secret, and he wants to share his secret among his friends in such a way that certain subsets will be able to recover the secrets, while other sets will not be able to learn anything about the secret. So instead of secret sharing, the dealer sends shares to every party, such that these properties will be satisfied. However, there are never too many homers. There could just more that will join, and also wants to participate in the sharing scheme. So the trivial solution would be to just reshare the secret. However, some parties don't want to do it all over again, while others may already gone offline and they don't participate at all. So one way to solve this is to just choose a big upper bound on the number of parties and do finite secret sharing with that bound. However, there are two issues. First, if we choose the bound to be too big, then maybe only a few parties arrived, and this means that the share size, that the shares that the parties received are much larger than they should have been. The other issue is maybe we chose the bound to be too small, and in this case, we're just back at the previous slide where there are too many parties that arrived, and this means that we'll have to reshare, and we want to avoid that. So to solve this, Komorgotsky, Naor, and Yogev introduced evolving secret sharing schemes, where here there is an infinite number of parties, P1, P2, and P3. The parties arrive one by one, where party PT arrives at time t. And when it arrives, the dealer gives it a share, and this share cannot be modified later. We define an evolving access structure to be a monotone collection of authorized sets, and we require two properties. The first is correctness, meaning that every authorized set should be able to recover the secret, while privacy requires that every other set, called unauthorized sets, should not learn anything about the secret. So what are the previous results? So first, I need to define how we measure share size in this setting. So the share size of the TIF party is measured as a function of T. So notice that this also means that the share size is independent of the number of parties that will actually arrive at the end. So this is an important part of the model. So Komorgotsky et al. Showed that any access structure can be realized with a share size 2 to the T minus 1. And they also showed in their work and subsequent work that some access structure can even be realized efficiently. However, last year, Mazor showed that this is essentially optimal. He showed an example of an evolving access structure where infinitely many parties must receive almost 2 to the T share size. But this still leaves a lot of open questions. For example, what classes can still be realized with non-trivial share size, where by non-trivial I mean 2 to the power of Ct, where C is some constant strictly less than 1. Some other questions we can ask are about natural classes, whether they can be realized efficiently. And we can also talk about lower bounds for interesting evolving access structures. So these are the questions we asked in this work, and we also provide answers to each of them. So let me tell you about them. So our first result about the first question is schemes for infinite branching programs. So first we define what an infinite branching program is. Essentially, it's a computational model that allows to compute evolving access structures. I will give a more formal definition later in the talk. But for now, you can think of it as a generalization of the finite version of branching program to the infinite case. We then construct an evolving secret sharing scheme for a layered version of infinite branching programs. And this construction also abstracts and generalizes all previous constructions. And finally, in terms of share size, we show that if we started with an LIBP, a layered infinite branching program, with a bounded width, then that results in a small share size at the end. So I won't show you the exact parameters because the theorem is too technical, but as an example, if we started with an LIBP whose width at layer T is strictly less than 2 to the power of 0.15 T, then we'll get something non-trivial. So this already answers the first question of the three that I showed you, where we identified a class of functionality, class of evolving access structures that can be realized non-trivially. But as another interesting example for evolving directed layered ST connectivity, which again I'll define later in the talk, this is an access structure whose finite variant was studied extensively, and we showed that if it is a layered version, then we can implement it, we can realize it with share size that is comparable to the finite case. Our second result is about 2-slice and 3-slice access structures, which for the finite setting were also studied extensively. So first, let me give you a definition. A k-slice means that any k plus 1 parties should be able to recover the secret. Any k minus 1 parties learn nothing about the secret, and a set of k parties may or may not be able to learn the secret. And this is formally defined using some hypergraph. So just as an example of a 2-slice, let's say that the set of parties that are authorized are P1, P2, or P2 and P3, or P3 and P4, and so on, and all finite sets of size at least 3. So all of these sets are authorized. So, for example, P1 and P3 should not be able to learn anything about the secret, but P1, P3, and P5 should be able to recover it. And we showed that for 2-slice and 3-slice, they can be realized with share size that is subpolynomial, which is also comparable to the finite setting, where it is also known to be subpolynomial. And additionally, we also consider what's called a dynamic threshold, which I won't have time to go into too much detail, but this is a natural generalization of the threshold, the access structure from the finite setting. And previous result already showed that this can be realized efficiently. We showed that this can be improved if we consider the very large threshold. And finally, we also present some lower bounds in our paper. We showed for directed ST connectivity, we showed that there are infinitely many parties that should receive share size at least T. And interestingly, as a byproduct, we showed that for the finite setting, there is always a party that receives a share of size at least square root the number of parties. And this holds for all secret sharing scheme realizing it. And we also have a second lower bound for k hypergraphs, where a k hypergraph just means that the minimum authorized sets are all of size k. Notice that unlike the slice access structure here, large sets that do not contain an authorized set of size k are still unauthorized. And here we show that the share size must be large. Specifically, we show that infinitely many parties must receive at least t to the k minus 2 share size. And what's nice about this is that it also matches the upper bound of the naive scheme for implementing this. So with the time I have left, I want to talk about the layered infinite branching program. So I'll do it with an example for free threshold. So pictorially, this is an infinite branching program. This is a labeled graph. And computation, it's labeled with either one or the parties. And computation for a set of parties A proceeds as follows. So we start the computation at the top at U00. And we can pick an edge if it is either labeled by 1 or by a party in the set A. And we say that the path is accepted if the path that we chose reaches a leaf. And finally, we say that the set of parties A is accepted if there is an accepting path. Also notice that this definition is inherently non-deterministic, since then we can choose, there are multiple paths to choose. And just as an example, if we took A to be P1, P2, and P4, then this is an accepting path. We choose P1, then P2. We can choose P3, so we go left, and then we take P4. And finally, just because I told you that I will define it, ST connectivity is defined using, again, with a graph, a labeled graph, but now each party labels only one edge. So this defines an access structure of ST connectivity. And with the time I have left, I won't have time to go into the full details, but I will just give you the high-level ideas of how we realize LIBPs. So we start by constructing, by transforming the LIBP into an infinite decision tree. So if we do this naively, then we'll get a very wide decision tree. So what we do with this tree is that we label its edges with a finite access structure rather than just parties. We then apply the result of K and Y to realize the infinite tree. This will create a share for every edge, which I remind you is labeled with a finite access structure. So to finalize the scheme, we share each of these shares using a finite secret sharing scheme. And this gives us the full result. All right, so to summarize, we considered evolving secret sharing schemes. We constructed a general scheme using layered infinite branching programs. Our construction abstracts and generalizes previous results. And it also provides non-trivial share size for many evolving access structures. We also showed improved constructions for dynamic thresholds with very loud thresholds. And we show efficient scheme for 2-slice and 3-slice evolving access structures that are also comparable to the finite setting. And finally, we showed lower bound for ST connectivity and hypergraphs. And that's it. Thank you for listening.
Any questions? If not, I have a quick question. So for any evolving access structure, we know the share size is 2 to the t and it's tight. What can we say about the layer infinite branching program? Does it mean for any access structure, I can write it in the LIBP and use your compiler? Does it give me 2 to the t?
You can always use this compiler, but some, like the Mazor access structure, for which you showed the lower bound, this would mean that the corresponding layered infinite branching program will be very wide.
I see. So I see. Okay. Yeah. Any more questions? Okay. If not, let's thank the speaker again.